Hello, welcome all. In this lecture, we are going to discuss about the conformational analysis or conformational isomerism. There is a difference between conformation and configuration. Configuration we already studied in last lectures actually. Configuration, that optical isomerism and geometrical isomerism, but conformation is something different. Can you just explain what?
These are two dogs actually.
Yes.
And in case of what is happening in case of configuration isomerism is actually connectivity. This is a three-dimensional arrangement is very different. Here, this dog have totally different arrangement. This the tail is coming here and its leg got backside, and yeah, so that if the dog to this dog, that is impossible. Almost we need some serious operation. Then only it is possible to go from here. We have to cut this and add it here, so like that only it is possible.
Yes,
in case of configuration isomerism also we have seen that without bond breaking, that is very difficult to go from one to another.
Yes.
And in case of conformational isomerism, it is standing differently, that's all.
Nothing but this is different movement of that dog.
Yeah.
Okay. Here in this dog, it's lying on the floor, and that is relatively unstable compared to when it is standing. The features are the same.
Some energy is applying means dog can simply stand.
Yeah.
That is very clear from this image, I think.
Yeah, this is a person with different postures.
Yeah, so if, by applying simple energy, he can move from different pose, from one to another conformation. He can
sitting,
change standing, and dancing.
Yes.
Where in case of configurational isomerism, what happened is the same persons have interchanged its leg and its hand.
Yes, here look at all the features are the same, but when it goes for a configurational configuration, it is that leg and hands are interchanged. So what is this conformation is this? In case of, if we are talking in the case of a molecule or in chemistry world, what is it? It is the rotation about some sigma bonds. The sigma bond can easily rotate, and as a result of that rotation, we can have different structures or different conformers. Okay. This is a pheromone molecule, and if you rotate along a CC bond, we can have
different structures.
This arrow is put there, and if you rotate along those CC bond, this one conformer is this, one conformer is this, and one conformer is this. So these are possible because of the free rotation about a single bond. Earlier we have discussed about the CC double bond rotation, no?
Yeah, that is that actually CC double bond is always having a restricted rotation. Here also we can see that this is always in this, here there is a double bond in this pheromone. Yes. This is always in its trans form, where hydrogens are located opposite to each other. In all conformations, it is in trans form only. So without a chemical reaction, this trans is impossible to make it into cis. Where in case of single bond, it is possible to rotate. And it is able to.
Why? Because in the case of double bond, that CC pi bond is there, that pi bond will break. So that is not possible there.
Yeah, that we have explained in geometrical isomerism.
We have to study about some conformational analysis of ethane, butane, and cyclohexane. So in this lecture, we will be talking about ethane and butane. We know the structure of ethane is this, CH3CH3, and we have a CC bond, and we can have EC rotation, or we can have a rotation about that CCC.
Yeah, we can show here.
So what is this? We are just rotating, or while rotating, what we are doing is that changing the dihedral angle between the substituent on one carbon with the substituent of the other carbon. Okay, that angle between two planes, that is nothing but the dihedral angle. We have already studied, or we have already familiarized the words staggered and eclipse conformation, no?
Yeah.
So this, while rotating along that CC bond, we can have the staggered conformation and the eclipsed conformation.
This is very clear if we see this through this Newman.
You can see only this one.
We can see through this CC bond. If we are seeing, means that will be very clear.
This is the Newman projection, where we will see first carbon and the substance on the back carbon. And so this is the eclipse conformation where the substituents on the second carbon, that is the back carbon, are just lying back side.
That is means 0 degree to each
0
other.
degree to each other. So as we rotate this the different angle, we can have this all are different. This hydrogen position is moving, no, and this all we can, if we rotate from 0 to 180 degree or 0 to 360 degree, we can have many conformers, and each conformers have different energy. Okay, so what we have to learn here is that what are the main different conformers and what about their energy. Okay.
So here this become a
staggered conformation. The staggered conformation means the substituents or the hydrogen atom on the back carbon are lying in between the hydrogen atom of the front carbon, or that is lying in between. That is staggered conformation. And in the case of ethane, this is the comparatively stable. This is a highly stable structure, or this is having less energy.
Because there will not be any
interactions. If in the case of eclipse means this hydrogen will have electrons, no, that atom will have bond, that bond, CH bond and this CH bond are coming parallel. So this bonding electrons can have a repulsive interaction. Negative. There are both negative charges, negative thing, so that can repel. So this structure is highly unstable.
Whenever it is in the eclipse conformation, that will be having a high energy because of the repulsive interaction between the hydrogens, and that leads the molecule
unstable.
Yeah.
So while rotating, we can have a conformer like this, an orientation like this, and we can have an orientation like the staggered conformation. Okay, so let us see the energy profile of which one have the energy, higher energy. So one more thing we have seen while showing this three-dimensional figure, we have seen this molecule through a Newman view, no?
Yeah.
So while dealing with the conformational analysis, it is better to see the molecule in the Newman projection. So what in the coming discussion and all, we will be talking the thing in the Newman projection. So this we have in the case of ethane, we have two conformations, that is staggered and eclipse, and the energy required to move from one conformer to the other conformer, that is called the torsional energy. And there is a strain in the molecule, and that strain is called the torsional strain, and the strain is due to the repulsive interaction or the repulsion felt by if they are in the eclipse conformer, these hydrogens are coming parallelly or back to back, and that repulsion is causing the strain in that molecule or the instability in that molecule. So if we give some 2.9 kilocalorie, the staggered conformation can change to eclipse conformation, or while going from eclipse to staggered, it will release that energy. Yeah. That way also we can tell. Okay. Yeah. Okay. So we can just show the three-dimensional view.
Yeah, actually this is very simple thing. We are having a graph here where we are having a degree of rotation in x-axis and potential energy on y-axis. If you see, this is our eclipse conformation, where we are having this two hydrogen, this red hydrogen, that is exactly 0 degree to each other.
Yes.
So it will be just like this.
Yeah. So this is like the bond angle or the dihedral angle is 0.
Whenever we are increasing this dihedral angle, then the many conformations are possible here
with different energies.
With different energies that you remember. And you see one more thing. If you keep this 0, then this bond angle basically from this hydrogen to this hydrogen, that bond angle is 120 degrees. And if you backside bond, that is rotating
only one carbon. Back carbon we are rotating. Yeah.
We can make this 60, and in 60 itself, many rotations, those things are possible only. Here many energy states are there. If this this hydrogen atom and backside hydrogen atom both are both are just overlapping. That is eclipsed form. In eclipsed form, that coming back to back, it will be having a lot of repulsion. Yeah, the repulsion is that CH bond which have electrons, and the back carbon also, that CH bond have electrons. So when these bonds come together, bond pair repulsion is there, and that is the reason why that conformer is in the higher energy. So if we are rotating that continuously to 60 degree, then it will be totally free from that. Not totally free, it will be, there will be some repulsion will be there definitely. So that will be very less for at 60, because this is the staggered conformation. Staggered conformation means that the hydro groups, the back carbon, the substituents of the back carbon is coming in between the substituents on the front carbon. And also, again, if we are increasing, means what will happen? This hydrogen automatically it will start trending, that start moving towards the next, and that bond pair repulsion, it will start. And that repulsion is called the strain caused due to that bond pair repulsion is called the torsional strain, and that energy required to overcome that, or the energy related to the torsional strain, is called the torsional energy. So in the case of eclipsed and staggered, eclipsed, here we have the bond pair repulsion, and the corresponding torsional energy for to overcome that eclipsed conformer to staggered conformer is the torsional energy, and here it is around 3 kilocalorie per mole. Yeah. So basically, this will be again rotating and staggered to eclipse. This is the 120 degree, and this is the conformation 180 degree. Yeah. So this is the, if we go for 240 again eclipse, yeah, then it will. This is the how the graph comes. Okay. So from important thing that we have to remember in this graph is that 2.9 calorie is the magnitude for that torsional energy. Yeah. And where required from to change from staggered to eclipsed. Yes. Whenever from eclipsed to staggered it is coming, that much energy it will be getting liberated also. Yes. Okay. Yeah, that's so all. That why the staggered is stable, because the less repulsion will be there. So that is the reason why the staggered is stable. Staggered conformation is the stable one. And next, let us see how the things in the butane case. Yeah, conformational analysis of butane. Yes. How it will change in butane case. Yeah. In case of conformational analysis of butane, here we are having 4 carbon atoms and 3 CC sigma bond. And think we are speaking only about the normal butane. Yes. So we are having 3 CC bonds are there. C1 to C2, C2 to C3, and C3 to C4. So if you see C1 to C2 and C3 to C4, both will always remain the same only. If you look at the molecule through C1, C2 or C3, C4, the new band projection will look like this. Okay. In this case, there are 2 conformations are possible in case of C1 to C2 bond. If you are looking through C1 C2 bond, means the first carbon will have 3 hydrogens, and the second carbon will have 2 hydrogen and 1 ethyl group. C2H5. Okay, this is the staggered conformation where the ethyl and hydrogen are anti or opposite to each other. Okay. This is the eclipse conformation, which where the hydrogens are eclipsing each other. Also, the ethyl group and the hydrogens are eclipsing each other. So when we rotate again, we will get an staggered conformation, and if the 60 degree further rotation will give, that ethyl group will come to the second. Basically, for this bond, C1 to C2 bond, we are having these only 2 conformations only. That will be exactly repeatedly coming only. Yes. But so, if we see through this bond, C2 to C3 bond, then we are having many conformations. Yes.
So that is in the C2-C3 bond. For the C2 atom, let us take it as one first carbon. So the two hydrogens will be two substituents and one CH3. Similarly, for the back carbon, also the three substituents where two are hydrogen and one is methyl group.
Yes.
So, if let us take the higher energy conformer starting. So this is the eclipsed conformation where
two CH3s are coming 0 degree.
Yeah.
That back to back.
So
and this will be the very high energy one. This will not be stable at all because of the
bulkier group. The CH3 is also a bulkier group, and thus repulsion will be more.
Repulsion definitely it will be more only.
Okay.
And if that is just rotating 60 degree, what will happen? Then this CH3 will come here, and it will form a gauche conformation.
The gauche conformation means it is a French word where the meaning is that left. Yeah. So that CH3 and CH3 are nearby, left, right side. Okay.
Again, we are moving 60 degree. Then we are getting this conformation.
This is also an eclipse conformation, but it is different from the first one. It's because in the first one, two CH3 groups are coming, but in this eclipse conformation, one hydrogen and one CH3 is coming back to back.
Again, we are moving the
group
front
carbon. Here the front carbon is rotating. Then we will have a CH3 in the opposite and this is the most stable conformer in the case of butane when we are looking the molecule through C2C3 bond.
Anti-conformer.
Yeah, anti-conformer. And why? Because there is no, the interaction is less.
It is minimized very much.
Yes. So when we rotate again 60 degree, we will have see this same thing, eclipse conformation as that in the third case. Then further rotation will give a gauche conformation where CH3 are coming nearby. Then if we have a further rotation of another 60 degree, we will have the eclipse conformation where CH3 is coming together. Eclipsed. So let us analyze the potential energy profile for different rotation around that second CC sigma bond in butane. So the first conformer is the eclipse one, where the dihedral angle between the two substituents on the two carbons is 0 degree, and here the CH3 is coming back to back. Exactly back. And also, so there will be high, the CH3 group is a bulkier group, so that will be, the repulsion will be more.
Here, because this CH3 interaction will be there, so
repulsion will be
more. So this will be having high energy.
Yes.
And whenever we are rotating this to 60.
Yeah, 60 degree, what we will get, that CH3 is
now in gauche conformation.
This is a staggered conformation, and if the CH3 is coming left to side by side, that is called the gauche conformation.
And if you are again rotating it into 120, again eclipse conformation.
But it is different from the earlier one, so that graph is little bit lower energy than the first one, the first eclipse conformation, that is the air structure. Here the eclipsing is between the hydrogen and the CH3. So further rotation to 180 degree will give the most stable conformation, that is the anti-conformation where the CH3 groups are coming opposite.
So that is having very low energy.
Yeah, so if you repeat this to 360 degree, the same will replicate. Okay, so here the energy, it will replicate, yes. This is how the rotation is happening. Yes, okay, it comes like that. This is the where 300 degree, then 360 degree, it will again come back. So the higher energy state. That is the eclipse conformation, and here the energy for changing from eclipse to the most stable anti-conformer or the staggered conformation is this 4.5 kilocalorie, and the gauche conformation and the eclipse conformation where the hydrogen and CH3 is coming. The structure E and C, that energy is 3.8 kilocalorie, and the energy difference between the gauche conformation, that is F and B, with the anti-conformation is only 0.9 kilocalorie per mole. So this magnitude you should remember. This value,
Potential
at least in
values.
any, don't want to remember in both units, either in kilocalorie per mole or kilojoule per mole. That is up to your choice. Okay. So this is all about the conformation of
Butane.
butane and ethane. Okay. Thank you.
Thank you.